Thank you. So so my name is Salvador Peña. I work at photrack, and at photrack we have developed different solutions, all image-based discharge measurements. So like the ones are fixed stations that they are continuously measuring. Of course, we have also the app that I'm going to present later, and also some software to do processing. And here are some numbers of sites that are on the upper left image that they are used where the app is used. Also some idea of how many measurement stations we have up to now and measurements that have been done. And on the lower image is the location of the fixed stations. So we have been, well, almost all our fixed stations are measuring at cycles of every 2 minutes, they are making a measurement. So then we've been collecting all this data, kind of almost continuous data. So we are asking ourselves, what can we do with this data if we can get more information out of this? So not just doing discharge calculations. So one of the advantages of these technologies that they are based on images is that we can calculate the flow velocity on all the field of view of the image. And for example, in this case, also we define a region of interest. And so we are measuring the whole velocity field on that region. And it's a 2D flow measurement. So we can see, and since we're measuring every 2 minutes continuously, so we start observing some changes in these surface velocity patterns. So our question is, can we learn something more, something in addition out of this information? And of course, we know that the surface velocity distribution and magnitude depends on the bottom of the river, if it is on the shape of the cross-section, on the roughness, if there is a rock. So again, our question now is, can we learn something else out of observing changes in the surface velocity? And specifically, we think that we might be able to see changes in the cross-section. So for this, I'm going to use an example of, I'm just going to use the data of one of our continuous systems. This one is located in Switzerland. It's close to the site of Meiringen, actually where Sherlock Holmes was killed. And this one has, so you barely can see it from that image, but so we have the camera, and then we have a box where, so all the calculations are done at the site. And on that box, we are doing, we have all the hardware that we need. This site is located downstream of a power plant, a hydropower plant, and they are, so this makes changes in the river, that the water level changes quite rapidly and very often. So we have changes of 1 meter 4 times per day. So I think that's one of, it's good, this site, because then we can observe all these changes, and then we try to, and then we can use this data to try to analyze all these changes in the surface velocity patterns. So here's a bit of a closer look to the system. So we have there is the camera, which has an infrared beamer integrated for the night measurements. And on the box, I mean, it's very small, but there is the modem, the PC. We have some, also, we have some analog outputs connected. We have also some external sensor, because to get the water level, because actually, so some of our stations do it optically, but in this case, as we can see in the image in the center, in the middle, it has some rocks, and it's not very well defined. It's not completely parallel, let's say, to the flow, the shore. So it's not ideal to conduct the optical level in this site. So that's why we have a radar that is also shown in this image. This radar is directly connected to this box, and also, so the system is telling, now I need a measurement of the level, and that is is fed into the calculations. So this is a time series, and the only purpose of showing this is that we can see those high fluctuations that they are happening like around 4 times per day. And they are around 1 meter in height, those changes. So for the analysis, we took 2 months of data. So those videos taken every 2 minutes during 2 months. And we can see a bit of the distribution of the water levels. So mainly most of those measurements were taken at a certain height. No? This is meters above sea level. So it doesn't say much, but it's a 714 meters approximately is where most of the time the water level is located. And then we do, so here's an example of processing of a video at a certain height. And we can see the velocity vectors, and the color depends, it's a representation of the magnitude. So if they are green, it's where the water is flowing more slow, and red is when it's moving faster. And on the plot on the right, we have this scatter plot, which each one of the arrows that they are on the image represents 1 dot on the scatter plot that we have on the right. So on the x-axis, we have the velocity, and on the y, we have the river width. So we can see the distribution of the velocities across the river. So this is another representation of the same thing, just it is rotated. No? Now I have the velocity on the y-axis and the river width on the x-axis. And this is, as you can read from the title, this is an ensemble of all the velocity magnitude from 1,927 videos that were taken at exactly the same height, plus minus 10 centimeters. No? So we choose a range, we look for all the videos that or processing that were in this range, and then we compile all that scatter plots in this plot. And we can see like, the way to read it is like, if it is red, let's say it's the most likely velocity according to the, where it is located on the across the river. Yeah, it's kind of a probability distribution. We just normalize it to have a better color coded. And this is done for different pins on the along the cross section. And in this animation, I hope it is rendered properly. It is exactly the same plot, but at different heights. So now the water level is going up, and we can see how the velocity, the surface velocity is changing. Of course, first it's going faster, the river is getting, or the water cover, the surface of the water is getting bigger as the water level increases. And probably here is a bit easier to see that. So now, instead of showing the probabilistic distribution of those velocities, I'm just plotting a line per different heights for the most likely to happen velocity for that height. So again, we can see that the water is going, the level is increasing, the velocity is increasing. And actually, we started seeing that the center of where the fastest velocity is located actually is moving to the left shore. But I think what is, for us, was a bit more interesting to do is to compare what is happening on the time, no? If this shape is changing. So we compile 2 months of data, and here is for the highest level. So actually, so we try to do those months divided in 15 days. So each line represents 15 days. But here is the highest level. So we didn't have that water height for that time. So here I'm moving down So the next one, we can see that we have a bit more data. And then again, the level down, and I see that now we have data for all those 15 days, for each of those different 15 days. But what comes interesting is on the lower levels, we can see that those lines do not match. They are not on top of each other anymore. So yeah, even on the lower, we can see this a bit more evident. Actually, well, it's a bit confusing to here see the color. So I summarized those I grouped them in three groups of 3 weeks, I think, each one. So we can see that the first one, that is this orange, that is from February to March, is flowing slower. And then the next one starts going faster and faster. And actually also we can see that the area covered is becoming smaller. So here is the question, if it is really telling us something, that something changed on the cross-section. So to me, this looks like actually this part of the cross-section, I think, is getting deeper. And so it's been eroded, no? It's been eroded. So most of the flow is happening in a smaller channel and it's flowing faster. So this is, we have not checked this on the field. We have not gone, I mean, we should go and take again the cross-section measurements, but it seems that is an indication of what is happening. And I think that can have a huge impact on the calculations, because we are using the velocity area method. And if our area is changing, of course, all our discharge calculations are going to be off. So the idea here is to first to get an indication that something has changed, and probably that the cross-section has to be updated. But one step forward, it could be, can we use this information to update the cross-section? Can we say, oh, this change in velocity means that the cross-section got, let's say, 5 centimeters deeper? So that's what we are trying to see now. So that's all. Thanks for your attention. Do you have any question?
Yeah, okay. Thank you, Salvador. Really interesting. I like the approach of, seeing what new learning you can get from the data that you're collecting. So very interesting insight. We've had a question from Rob Thomas. Rob, do you want to unmute and ask it, or do you want me to ask it?
Sorry, I'm eating an apple.
Well, I can ask it. You can ask it more precisely, with more eloquence than I can.
Okay, I'll try and speak.
Sorry, Rob.
The spatial binning approach that you used for a set elevation, water surface elevation, I wondered if you could look at the deviations from that, from the average, and extract something about turbulence.
Yeah, I guess. Yeah, I'm not, well, first here's just, so I have not tried, right? So that's what I'm thinking, if how to do this. So all this analysis was done on just only on one component of the velocity. But yeah, I guess we could, for example, I don't know, in that image, I don't know if you realize, actually there is even a rock. And that rock, we can see it on, we see the footprint, no, of how the level is changing, and we can see that rock, what is the effect. So yeah, I think we could do it, if that's the question.
Okay, thank you. And we have a question from Saksham Gakar. Can you elaborate on the working principle behind the surface velocity measurements? So I think, how are you deriving the surface velocity?
So we use a cross-correlation technique on the back. No? It's a LSPIV. The only thing that is that we do different from the standard LSPIV, that we just apply some special filters to remove some not moving parts of the image. Also, we can get rid of a bit of glare, things like that. So also from the bottom of the river, we can filter it out. So also we can do some measurements a bit more on the low flow, but I mean, it's a cross correlation technique.
Yeah, okay, based on imagery, of course. Julio, do you want to ask your question, or do you want me to ask it? Go on, you can unmute.
Yeah, I can, yes. I think you already answered part of it. I was just wondering, because it looked like the surface was quite wavy.
Yeah.
So do you account for the influence of gravity waves, and do you separate them from the actual flow velocity?
In a very empirical way. So I wonder if you, in this, on the scatter plot, if you pay attention, there are two colors. There were actually two dots, one that was red and one was black. And actually we're trying to account for those gravity waves. But it's a very empirical way. So from all this data, we have seen where we are debating. We are trying to see which type of waves, more like on the shape that they have, how they are affecting the velocity vectors. And then we filter or we correct for them. But I think a more formal approach could be better. No? We're working on that. Like the one you presented, no? The wavelength.
There is a paper where they did something similar looking at the PDFs of velocities to separate the turbulence from waves as well.
Yeah. Yeah, I mean, also it's like all this question, like on this PDF, it is all the scatter, is all, we see that the main one is really because of variability or some waves or some other phenomena.
Okay, and with time is always slightly tight. So do you want to go into your quick demonstration, Salvador?
Yes. So I want to share my screen again.
I think we can give you about 7 or 8 minutes if that works for you.
Perfect. So this came a bit just now very sudden. So thanks for making me a bit of a space to show this. I'm going to try to share my screen. So do you see it now?
Yes, I'm seeing that.
So now, as you can see, I'm just showing my mobile. So here is the discharge app. And actually, just going to do a very fast demo of the app. And on the app, so all runs on the mobile. So all calculations are done on the Android smartphone. So because I cannot go to a river, I have already a site that I went to visit. It's very close to our office, actually. So what I'm going to do is I'm going to reprocess that measurement that I already took, just to measure, just to show how it works. So first, of course, I need ground control points as any other image-based technology. So I wonder if I'm going to move this. So you can see there. So there's one marker that was already, of course, we set up that site already before. So we measure the coordinates of 4 ground control points. And we can do it with 4 because we also have information about the orientation of the phone because we read that from the gyroscope. So I have the 4. So the first thing to do is I just tell where on the image they are by moving these markers. No? So I just selected where they are. So I can go one by one and I move and then I select them. Once that I'm happy on the location, I do. And now what it is doing the camera calibration. So now it's done with the camera calibration. So here manually, I have to tell where the water level is. So I can zoom in into the image. And on the right, you can see the water level changing. If I say the water will be here, will be at 1.27 meters. Yeah? So I will move it up until it matches the intersection between the water and the cross section. So it's around that. So I said I check, and then I actually here you can see that says estimated discharge, and that is because we have a rating curve inside. So now it's reading the rating curve and gets that result. So I can actually already upload that result to the cloud because all this is connected to an API and we have a web portal where we can see this directly, or I can push into process video. So now this is processing the video and it's all done I don't know know if you see my, but it's all done in the phone. No, there is no data connection. It's not data going out, nothing. And this is all real time. No, it's just processing here on my 6-year-old phone. And then we have to, so this is like a 20-meter wide river. And after, I mean, you could see, no, after 30 seconds, I can see the discharge. And again, I can just click a button here and data is uploaded to our cloud database that can be accessed via also a web portal. Yeah, so that was a very fast show of the app.
It's very nice. With the fast demonstration shows how fast the processing is. So, and yeah, you're saying your phone is about 6 years old?
Yeah, it's a Samsung Galaxy S7, I think.
So it's going to race away on some of these modern, but it's just to clarify, it's Android only. There's no iOS.
Yes, only Android, and that, I mean, was actually that was chosen on purpose at the beginning because that was developed in the framework of a project that was financed by the development agency. So it was to deploy in some African countries. So we wanted to go to the cheapest option.
Yeah. Okay. And there's probably quite a lot of interest in the app. Is it available? Is it freely available, or is it something that people pay for, or what's the status?
So there is different plans. So there is one that up to a certain amount of measurements for free. Just can go to Play Store and download it. And then there are plans. So for more measurements, there is a plan that has to be paid, and that cost depends on the country. So again, we are trying if so the World Bank has a ranking of 4 different levels of the countries, and the price is a scale depending on the country that you are located. The only thing, if you use it, so what we have seen is it's kind of a behavior nowadays that is an app. You install it for free, you test it for 30 seconds, and if it doesn't work, you just throw it away. It's like a kind of a behavior of these days with the apps. No, so if really are interested, what I recommend is that we have many tutorials that really take time to check the tutorials. You can test that on your office. Wherever you are, you can test it before going to the field.
Yeah, cool. Okay.